everyone. Today in this video we are going to discuss some transformations of functions, and I will try to include as many transformations as possible. At the moment we have the following translations in our syllabus. We have reflection, rotation, translation, enlargement, stretch, and shear. Out of these possible transformations, what we are going to discuss for the functions, for the graphs of the different functions, we are going to discuss reflection, translation, and stretch. So these are the three transformations that we will discuss here. Now, before we move on, let's take a look closely at the function y is equal to f of x. Now, this x is regarded as or called as the input of the function, and the whole of f of x, or which we also call as y, is the output of some function. It's very important. What we are going to do is we are going to add subtract in the input, or we are going to add subtract in the output, or we are going to multiply by some number in the input or the output. These are the possible transformations that we're going to discuss. Similarly, if we multiply by a negative number instead of any number, let's say multiply by -1, again we are talking about doing it in the input and output. And then you will see what are the different consequences of each of these. Right, so to sum it up, we have addition, subtraction, change of sign, and multiplication of some constant, and they are done in the inputs or in the outputs. Let's take a look at these transformations. I am using this My iMaths website here, and let's start from the beginning here. Okay, so this is the original function. F of x is equal to x squared, and the table and graph of this is shown here. And then we have another function g of x, which is made by adding something to that original function x squared. Now what we do is, if we add some number to this output, remember f of x is the output, so if you are adding something to the output, the function is simply shifted upwards. Now you might think that it is shrinking or getting smaller, but if you look at the values are, for the original function we have 9410149, and for the new function g of x we have the same when this is 0. But when we add some number to the output, these y values are increased by 1. You can see clearly here 9 is now 10, 4 is now 5. So this is how we know that it's getting shifted, and properly using the word is translated 1 unit upward. And similarly, if you add 2 to the final function or to the output, you are shifting it 2 places upwards. You can see by keeping track of any of the points. In this case, the turning point, which is at 0, 0 at the moment, is the easiest to track. Otherwise, you can use any other point on the graph and keep track of that. So if I add something, you're shifting it, you're translating that function to one place upward, and now that turning point, instead of 0, 0, is now at 0, 1. Similarly, if we go in the other direction, let's say if we subtract from the output, what happens? The same graph is now translated that many units down. So if it is -1, the original graph is now translated 1 unit down, and if it is -2 from the output, the original graph is translated 2 units down. And you can see from the values as well, originally it was 9 when x is -3, and now it is 2 less than that. And you can see that the final value of the function, the outputs are all reduced by 2. Hence, what we see is, what we can identify from here is that whenever you are adding or subtracting to the output, you are getting a vertical translation. Let's proceed with that. So if C is positive, we get translation upwards, and if C is negative, as in this case, it is translated downwards. So let's update our table. When we are adding something to the outputs, we are getting vertical translation. For plus A, it moves upwards, and for minus something number, it goes downwards. It's also a good idea to keep track of these uh, points. So let's say originally we have any point xy, as I've indicated here. If you're moving upwards, the value of x doesn't change, but the value of y is increased by that much. You can see from the graph that the value of x isn't changing. If you look at this turning point, it's 0, and you move it up or down, you translate it up or down, x remains x, the same value, but the y coordinates are changing. So here we have a change in the y coordinate. Again, here we have a change in the y coordinate, but this time this is being translated down. So this is y minus a. That's the most generalized way of communicating. When a vertical translation is done, what you're doing is you're changing the y coordinates by addition or subtraction. Now let's move on to another case when we are adding or subtracting something in the input of the function. Previously we were doing changes in the output. Now let's see what happens when we are adding subtracting in the input of the function. Right, so the original function is I'm trying to use as many different graphs as possible, so that when we say transformations of functions, we are doing it in the most generalized manner. Instead of sticking to just one graph or one function, we have a variety of functions in our discussion today. So g of x is obtained by, as you can see, x is replaced by x plus a. So if I were to write g of x for this, what would I write? G of x is equal to f of x plus a as indicated. Now x is replaced by x plus a, so that will be x plus a whole cubed. If our original function is x cubed, then g of x is obtained by, let's say, adding some number to it, and so x is replaced by x plus a. So what you're doing is you are changing the input and adding something to that function. Let's see what the changes are here. I would like you to guess, if you are adding some number, where would it go? And the options are either forward or backward. Contrary to most of our assumptions, if we are adding something in the input, let's say plus 1, the graph is moving backwards. Normally we would expect the graph to move forwards for the plus, but that's the opposite case. Similarly, if I have the original function again, the subtraction of any constant results in the graph being translated forwards. So this is what we can conclude from here. If A is positive in this, if A is positive, the graph is translated left by A units. Left means going backwards from 0 on the negative side. So if you are adding some number, if A is positive, then you are translating it left. If A is negative, you are translating it towards the right direction. So x plus c, it means it will be going backwards, and here if you are subtracting something, it will be going forwards. I think these arrows are quite a very precise manner of communicating. Now let's see the point. This time it's just horizontal translation, moving left to right, so no upward movement. That means the y values remain the same, so I'll mark here. Now, if x plus c, as I said, it's going backwards, so the x coordinates are decreased by that amount. Similarly, if it is x minus d and you're moving forward, so the new x coordinates are obtained by adding that d to the original ones. Let's move on to the next transformation, and this time we have the cos graph. It's a trigonometric ratio, cos of x. Let's see what happens if we just reverse the sign of the output. Remember, when this f of x is the output, and if you are reversing the sign by reversing the sign of the output, let's see what happens. G of x is the original one. If you try to remember its shape, it's just like the downhill and then back up again. It's this valley that you see here. And if it is g of x is equal to negative f of x, now you see that instead of the valley, now you're getting the top of the hill. See, what it is mean? It means that the original graph is being reflected in the x-axis. Let's see the y coordinates here. For original one, when x is 0, f of x is 1. And now if you're reversing the sign of the output, means you're reversing the sign of the y values. It's minus 1, minus 0.7, and so on. So simply, all the positive y's are getting negative, and the negative y's, all these negative y values are becoming the positive y values. Hence, when you are multiplying the output by a negative, you are reflecting in the x-axis. So simply, the graph of negative f of x is a reflection of the graph in the x-axis. Now, let's fill out the table. If it is negative f of x, it means you are reflecting in the x-axis, reflection in x-axis or about x-axis, and the points. You can see from here that the x values don't change. You are using the same x values, but just a reverse in sign of the y values. So x and y values are reversed in sign. Let's see the other case when f of minus x means you're reversing the sign of the input. So there we are. Now we have another function, that's the exponential function, and this is the original one, a 2 power x. This is how it is, how it appears on the graph. And if we now reverse the sign of the input, what happens? As you can see, this light pink line is the original graph, and now it is being reflected in the y-axis. The new position is this one, and you can see that all the y values remain the same, but the x values are reversed. So what we do is we are reversing the sign of the input, and we're getting reflection in the y-axis. The graph of f of minus x is a reflection in the y-axis. So let's put it down here. This is also reflection, but that's in the y-axis. And when you are reflecting the y-axis, the y coordinates don't change. Only the x values have their signs reversed. You see, x is replaced by minus of x. Okay, so we summarize. If you are adding or subtracting in the output, you are translating it up or down, right? If you are adding or subtracting in the input, you're translating it forward, but the way of remembering is the opposite way. If it is x plus a, it will move backwards, and if it is x minus a, it will move forwards. When you are changing the sign or reversing the sign of the output, it's reflection in the x-axis, and when you're changing the sign of the input, it's reflection in the y-axis. So these four transformations are what we have done so far. Let's do this simple practice. If g of x is equal to f of x plus 1, you see we are adding something to the output of the function. It means the x value, which is minus 1 here, that remains the same, and the new y coordinate is increased by 1. So negative 3 plus 1 is negative 2. F of x minus 9. I hope you can guess this transformation. X minus 9 means it will be translated 9 units forward. So the y values remain the same. And minus 9 means minus 1, and then 9 places forward you get to positive 8. Then the next function is negative f of x. This is the original one, and there's a point on this function. If you are reversing the sign of the outputs, means multiplying the function by negative means the reversing the sign of the outputs. Only uh, the x values, the x coordinate remains the same, and the y value has its sign reversed. It's a reflection in the x-axis. Similarly, if you're reversing the sign of the input, so now it's positive 1 here instead of negative 1, the y values remain the same. There we are. Let's check. Yay, so we got all correct. And so this is translation upwards, this is translation forwards, this is reflection in the x-axis, and this is reflection in the y-axis. To sum up the four transformations that we have discussed, we have got this. We have an original function f of x is equal to x squared. If we reverse the sign of the output, it's reflection. If we reverse the sign of the input, its reflection in the y-axis, but for a parabola, it doesn't. The image and the object are overlapping, so you can't see it. If you add or subtract something in the input, it's translation forwards or backwards. If you add, it's translation backwards. If you subtract, it's translation forwards. Similarly, this number gives you a translation in the vertical direction. So let's reset that. And the question is, turn the graph upside down. If I have to turn the graph upside down, it means I'll be reflecting that in the x-axis. And how do I reflect? By reversing the sign of the output. Make the turning point 0, 2. Currently, this turning point is 0, 0. We want to make it 0, negative 2. 0, negative 2 is simply translation down by 2 units. That's a vertical translation, and vertical translation is obtained by subtracting or adding in the output. It goes 2 units down, so now you can see that the turning point, the new turning point is 0, negative 2. Let's reset that as well. The last one is make the turning point negative 3, negative 4 and turn the graph upside down. So first of all, we have to make the turning point negative 3, negative 4. The order of the transformation is quite important, so we follow the same order as given. Make the turning point negative 3, negative 4. Negative 3 means from 0 it's going backwards, so I'll have to add 3 units. And then negative 4 means it's going down, so I'll have to subtract from the output 4. And now you can see that the new turning point is at negative 3, negative 4. And now we have to turn the graph upside down. If I have to turn the graph upside down, I will be changing the sign of the function. And there we are. Let's try another set of instructions for a different graph. It says turn the graph upside down. If I have to turn it upside down, it means I'll be reflecting in the x-axis. And if I have to reflect in the x-axis, I'll simply reverse the sign of the output. And there we are. Make the turning point 1, negative 1, negative 1. Currently the turning point is 0, 0. We want to make it negative 1, negative 1 means 1 unit backwards and then 1 unit downwards as well. So for downwards, I'm going to subtract from the output. So now it's down at negative 1 and I have to make it at negative 1. So moving backwards, I'll have to add 1 to that. And now you can see that the turning point is negative 1 and negative 1. And then reflect the graph in the y-axis. If I have to reflect in the y-axis, that's an very easy task. It's simply reverse the sign of the input here. So if I reverse the sign, that is reflection in the y-axis. All right, so now we have another function. This is the graph of, you might have guessed by now, this is the graph of sine of x from negative 180 to positive 180. And this is how it looks like. The first is turn the graph upside down. If I have to turn it upside down means reflection in the x-axis, and that is obtained by reversing the sign of the output. There we are. Okay, move the y-intercept to 0, negative 3. The y-intercept is at 0, 0. We want to shift it at 0 and -3, so it's just shifting it downwards by 3 units because there is a y-intercept that is being changed. So from 0, it's now going down. And how do you translate it vertically? That's by subtracting or adding in the output. It's going down, so I'll be subtracting 3 from that. And now you can see that the y-intercept is at 0, -3. Then it says reflect the graph in the y-axis. In the y-axis, all the x's are reversed in sign. It means the input has its sign reversed, and this is what you see. The red one is the original one, and now it is being reflected. This point is reflected in the y-axis here. Let's do another practice for an exponential function. This time we have an exponential function, which is another type of function. We have turned the graph upside down. If I have to turn it upside down, you know what we will do? We will reflect in the x-axis, and reflection in the x-axis is obtained by reversing the sign of the output. I'll show you here, and in order to show you both of them together, I'll use this. So the red one is the original one, and now you reflect it in the x-axis. This is how you do it, and you achieve it by reversing the sign of the output. Now move the y-intercept to 0, -3. 0, -3. Currently the y-intercept is at 0, 1, and we want to move it at 4 places down to -3. So if we have to do a vertical translation, we add or subtract in the output. We have to go down. That's 1 unit down, 2 unit down, 3 unit down, and 4 units down. Now you can see that the y-intercept is at 0, -3. So we have to go 4 units down because it was already, the original graph was cutting at 1, and so to achieve a -3 we had to subtract 4 from it. And lastly, reflect the graph in the y-axis. If we have to reflect the graph in the y-axis, we have simply to reverse the sign of the input here. Let's take this example. This is the original one, and this is the reflected in the y-axis. And how do you achieve it? You reverse the sign of the input here. So guys, I hope the first 4 transformations are quite much understood. That is translations and reflection. Now the next phase of the transformations is vertical stretch and horizontal stretch. So we will again use this my IMath site, which is quite helpful for us right now. And let's see what happens. Right, so we have this function. This is the graph of cos of x. As you might know at this stage, this is how it looks like. The maximum value is 1 for cos, and the -1 is the minimum value, and it completes its one wave at 360, 90, and 270 are its zeros, and 180 is its minimum point. It has the minimum value at 180 degrees. Right, so what we have to do is see the changes if we multiply a number which is greater than 1 with the output. F of x is the output. So if we are multiplying a number that is greater than 1 to the output, what happens? As you can see that it is being stretched along the y-axis. Now when you say stretch along the y-axis, it means you are moving away from the x-axis. So when you say that you are stretching along the y-axis, it means you are stretching in these directions. Or in other words, you are moving away from the x-axis. That's the stretch along y-axis. At the same time, if you are moving towards the x-axis, you will call it as a compression. It means it's like being pressed down towards the x-axis. Okay, so let's see the website here. What we see is it's being stretched along the y-axis, and this is done by a factor. I'll put it back to a is equal to 1. This is the original graph, and you see that at x equals to 0, y value is 1. And if I multiply that by 2, the new value of y is 2. It means what you're doing is you are multiplying the original number, it is simply 2 times the original function or is original output. So if we try to sum it up here, what happens is the x coordinate remains the same and your new y value is being multiplied by the stretch factor. So the x value remains as it is and the y value is being multiplied by this number a. That's the stretch factor. Now if this value of a is greater than 1, it will be moving away. This is when you are having a greater than 1. And if a is less than 1 but still it's greater than 0, that's our next case, the point will still be the same, but we know if a is between 0 and 1, it will be a compression, and this will be a stretch along y-axis, and this is a compression along y-axis. All right, let's see for a few more values of a. Let's see we have 0.75 times f of x. The values are being multiplied. Again, the relation is being is of multiplication. So you can see that the values of I or the graph is being compressed vertically. Let me bring it back to the original one. So if we are having a which is less than 1 but greater than 0, this graph is being like pushed towards the x-axis, as you can see, and we call it the compression. This is the compression. So stretch along y-axis is when a is greater than 1, and compression along y-axis is when a is between 1 and 0. Next step is, what if we multiply a number in the input of the function? The previous was we multiplied a number in the output of the function, and now we see the changes that are done by multiplying a number in the input of the function. So here we have the sinusoidal curve of sine x. This is again a wave nature. Sinusoidal curves are the ones which repeat themselves after a certain amount or certain angle. So this is the graph of sine of x, and now we see the changes. Let's say if we are making a is equal to 1 and now a is equal to, let's say, 1.5. What happened? You can see that the original graph is now being compressed. Previously the wave was being completed at this point. I'll bring it back. So this point when one crest and one trough is completed is here, and now if you are multiplying it by a bigger number, the number bigger than 1, this number, the same point is being pushed towards the y-axis. And if I do it 2, you can see that instead of 360, the wave is being completed in half the same distance. Now we have two waves in the same interval, and each wave has its wavelength. The wavelength is now being halved and the number of waves is being doubled. What would you say in terms of transformation terminology? So we had the original function, and now this was being compressed along x-axis. It is being moved towards the y-axis. So what happened? The y values remain the same and the x values are now being divided by this stretch factor. Whatever that number a is, you're dividing by that number. See, as you can see that this is the original graph. Now the wavelength is being divided. This distance of this point, just keep track of this point where it completes its one wave. This distance is being divided by that number. The input is multiplied by 2, so that distance is now halved. So the relation is being of division. X over a is the new x coordinate, or if you keep track of a point, and the y coordinate remains the same. And so when you are doing the horizontal stretch, that is brought about when you multiply the input by a constant number and that number is greater than 1, then it's a compression along the x-axis. It means it is pushed towards the y-axis. Similarly, you can guess from here that if the number is between that, it will be a stretch along x-axis. In other words, it will be stretched away from the y-axis. That's the stretch along x-axis. It is stretched away from the y-axis. Let's see from the simulation as well. So this is the original graph. If we are now using a number that is less than 1 but greater than 0, you see that the wave would be completed somewhere here. It means it is moving away from the y-axis. And now you can see that the whole wave will be completed in somewhere here at 720 degrees, and just half of the wave is completed at this. So again, our uh, our point is communicated in the same way. The point is divided by that number, and that completes our investigation of transformations of functions. We use different functions. We use exponentials, we use trigonometric, we use parabolas, and we can involve more, but I hope this is quite a good investigation and summary of the transformations of different functions. The summary of this, the main point is that you remember where you are making the changes. Are you making the changes in the input or in the output? And that is the best way to remember. Okay, so now we move on to a task that I selected from the MYP. And this says f of x is 4x minus 2 is the original graph. And the graph of f of x is translated by the vector. Remember, the first one is walk, and the other one is telling you to climb. If this is a positive number, it means forward. So we are going to move 1 unit forward, and this is a positive number, so that's 3 units upward. Looking from this summary, whenever we have to move forward, that's the horizontal translation, and we have to change in the input. So we change in the input here. If it's one walk forward, you will have to replace x by x minus 1 to get it moved to 1 unit forward. So I'll replace x by x minus 1 everywhere. That's 4x minus 4 minus 2, that's 4x minus 6. That's x. So what we've done is we have moved it 1 unit forward by subtracting from the input, and now we have to make it shift, translate up by 3 units. So it's simply whatever that function is, you add to the output. And all of this is increased by 3. So our new function is 4x minus 3. So I'm using Desmos for this. The original function that we had was 4x minus 2. Let's graph it here. Y equals to 4x minus 2. That's our original function. And then if we have to translate it by 1 unit forward and then 3 units upward, so this is all the algebraic manipulation that I did. I replaced x by x minus 1 for moving it forward, and I'll label it here. That's the horizontal translation done. And then for translating it upwards, we have the vertical translation done here. The next graph is 4x minus 3. So let's take a point on this graph and the original one. Let's say, okay, next up is we have the original function f of x is equal to x cubed. And we are again asked to find the equation of the image when f of x is translated by the vector -2 and 3. So I'm going to indicate both of the transformations. Let's call the new function as g of x. So g of x is by doing these transformations. What we will do is, if this is translation backwards is done by adding something to the input. So we have to move 2 places backwards. So I'm adding 2 here. That's the backward translation. And then for upward translation, I'm adding 3 to the function. And now we simplify. F of x is x cubed. It means now we will have x plus 2 being cubed and then increased by 3. If we expand it, this is x cubed plus 2 cubed. It's okay if you don't know the identity, you can multiply it manually, but I'm using an identity here. So 3 times x squared times 2 plus 3 times x times 2 squared, and then all of it is by increased by 3, this 3. If we simplify that, we get x cubed plus 6x squared, and this is 12x, and then 11. This is the equation of the new function when it is being shifted 2 units, translated 2 units backwards and 3 units upwards. Now what I'm going to do is I'm going to check my graphs, and here we will be using Desmos for the checking. First graph is y is equal to x cubed. If you use the board here, y is equal to x to the power 3. This is our original. Let me zoom out so that you can see. Alright, the next function is that we obtained. If I could just simply show directly the transformations, then that would be a good idea instead of simplifying that. So I'm going to replace x by, it says you have to move 2 units backwards. So 2 units backwards means increase the input by 2 and then 3 upwards, so that's plus 3 to the output point. Let's just keep track of the turning point. The turning point here is shifted 2 units backwards and then 3 units upwards. So we know that our translation is correctly done. Just for the sake of it, let's see if this function is also correct. X cubed plus 6x squared plus 12x plus 11. So you can see that the blue graph and the green graph are at the same position, and that means these two are equivalent. These are the same function expressed in different forms, but the idea is that you are moving 2 backwards, so you're adding to the input, and if you're shifting it up or down, you're adding it to the output. It says reflect f of x in the x-axis. Remember, when we have to reflect in the x-axis, it's simple. Reverse the sign of the output or the whole function. I will do minus times f of x. When you multiply by a negative, it simply reverses the sign of every term. And there we are. Now let's verify for our, alright. So the purple one is the original graph, and now this is being reflected in the x-axis. The x coordinate remains the same, and the y values are reflected, are reversed in sign. So that's correct as well. Let's move on to our next transformation. This time we have to reflect it in the y-axis. When you have to reflect in the y-axis, what we just concluded from the above discussion was you change in the input. So I'm going to do f of minus x, means I'm going to replace x by minus x everywhere, or change the sign of the input. And so you will have negative 4x, negative 3. Let's take a look at this. So if we have the same function, right? So now it's being reflected in the y-axis. So guys, this is a short summary of the transformations of different functions that we have discussed. We have made that chart of transformations. I hope that will be helpful for you. So guys, now we have a task of MYP that is related to criteria B and C. Criteria B is patterns. Here we are observing some patterns and then we are going to generalize them. The criteria C is related to communication. So we will be using mathematical terminology and using the symbols as well. So here we are, graph of a quadratic function. I've displayed different pictures of the same quadratic function. This is the original function. It can be translated backwards, translated forwards, or it can be reflected in the x or y axis. It can be stretched in the x or y axis. So there are different transformations that we may come across. The first part is you must investigate each pattern and explain the reasons for the pattern. So to save time, what I've done is already used Desmos and graph the 3 functions here. First one is y is equal to x squared, and you can see that this is the red one. That's the red graph. Then we have y is equal to x squared plus 3. That is shifted 3 units upwards. That's our blue graph here. The next one is x squared minus 2. So the original graph x squared is now shifted, translated 2 units down, and hence the green graph is this. What we notice is that when we add or subtract from the output of the function, what do you mean by output again? Y or f of x. So when you add or subtract from the output, you observe a vertical translation. We discussed the 2 cases. If y is equal to f of x is our original one, then y is equal to f of x plus a results in upwards translation, and y is equal to f of x minus a. Again, we are subtracting from the output here, minus a, that's downwards translation. Let's say if xy was the original point here. Now, when you are shifting it upside down, up or down, you are not changing the values of x, you are just changing the values of y. So when we are translating it upwards, the x remain as it is, but the y coordinate is increased. Similarly, for downwards, it's decrease in the original y value. So we can definitely communicate in a better way if we keep track of these points. The original one was x, y. How was the axis of symmetry? Now for a parabola, you must again know that whenever you make a parabola, it's always a symmetric curve. And the line of symmetry for this one would be somewhat like this. This is the line of symmetry, and it's the same half being reflected on the other side about this line of symmetry. Let's call it LOS. So the line of symmetry is not changing, it's just moving up or down along the same line. So the line of symmetry, no change. Generalize the pattern that you notice from this step in the investigation. This is what we are expected to generalize, and we have already done that. Let's move on to the next part. Okay, so again, I have already graphed these using the Desmo software, and I'll label the colors of each of these. You see the red one here, the one in the middle, that's the original one, y is equal to x squared. And then y is equal to x minus 2. That's the opposite way of remembering. If you are subtracting 2, then it goes that many units forward. So if the red graph is moved forward, we move on to the purple graph here. So this is the purple graph. And similarly, if you're moving it backwards, the black graph here is the y is equal to x plus 3 whole square. And for that, what we do is the original graph is either moved forward or backward. So what we notice here is addition or subtraction in the input of function. That's notable. Input of the function causes horizontal translation. Now, what is this horizontal translation? It's the reverse way of remembering. So if we have y is equal to f of x, then y is equal to f of x plus a is translation backwards. That's the opposite way of remembering. If you're adding some number, you are translating it backwards or to the left. Similarly, if you have y is equal to f of x minus a, then you are shifting it. You're doing the translation in the forwards direction. So that's our generalization. If the original point is x, y, the translation backwards, x is reduced by that much. So what we will write is x minus a, the y coordinate remains the same. And similarly, if you're moving forwards, the new x value is x plus a, and the y value remains the same. So again, using these reference points and what happens to the points is quite a very good way of remembering the translation. So addition and subtraction in the input of the function causes horizontal translation. Let's move on to the next one here. Okay, so what we've got is a combination of horizontal and vertical translations. As you can see, something is subtracted from the input and something is added in the output. If I say the translation vector, then the translation vector is minus x minus 4 means 4 forwards, and then plus 5 here is 5 upwards. So I'll try to make the sketch of this. The original curve is somewhat like this. That's the red one. And now after doing these translations, it's 4 units in the forward direction. So first of all, I'll shift it 4 units in the forward direction like this. So that is being dealt with. And then I'll use another color for doing the vertical translation. That is, this green graph is now shifted 5 units upwards. So somewhere here, it will be somewhere here. Right, so this is just a sketch. What I've used is the actual graphing software, and you can see this is the origin and the original graph that was having its turning point first at 0, 0, as now its turning point at 4, 5. It's moved 4 units forward and 5 units in the upward direction. I hope that makes sense to you. So what we have done is horizontal and vertical translations for this task. To sum it up, this is again doing nothing else than adding, subtracting in the input and adding, subtracting in the output. So what we are concerned here is with the translation. So if we have the general form equation x minus h whole square plus k, then hk will be the translation vector. It means we will translate using this vector. And it is notable that when you're comparing it, you're comparing with x minus h whole square. So something that is subtracted from x is your h value. Let's say if you get x plus 2 whole square minus 3, then your translation vector is not 2 and negative 3. The translation vector is negative 2 and negative 3. It means it will be moving backwards and downwards. When you add something, it moves backwards. So hk is the translation vector. So hk is the translation vector where h is responsible for the horizontal translation. And if h is greater than 0, so it will move forwards, and if h is less than 0, then we will be moving backwards. All right, and the next is k. K is responsible for the vertical translation, and when k is positive, when k is greater than 0, it's upward translation, and when k is less than 0, it's downwards. The next part of this task is sketch the graphs of y is equal to x square, half x square, and 2x square. Now, when we go to the graph, I've already used Desmos to plot these graphs, and I've done it on the same grid, so you can compare with them. Y is equal to x square is the red graph here. When you are multiplying it with a number that is half, that is a number which is between 1 and 0, then what happens? Then it is being compressed along the y-axis, as we have already seen in the transformation summary. This is a compression. So compression means, in other words, it becomes fatter than before. It's slow to rise and slow to fall than before. So the blue one here is the graph of y is equal to half x squared. Similarly, if you're multiplying a number with the output, which is greater than 1, then that number speeds up the behavior of the graph. It speeds up, so it's quicker to fall and quicker to rise, and that clearly means the graph of y is equal to x squared is the green graph here. What we notice from here is that first of all, how is the axis of symmetry? When you're stretching along the y-axis, you're not doing anything to the axis of symmetry. So the axis of symmetry is not affected. That's clear. And what do you notice about the graph? So let's try to summarize here. When you are having the original function f of x, and then you're multiplying this f of x, the output, by some number, then there are two possibilities. First of all, if a is greater than 1, and if a is greater than 1, it will be a stretch along the y-axis by scale factor. Scale factor means it will be multiplied by that number, scale factor a. As you can see, for the green graph here, this number that is multiplied is bigger than 1, and so each value of the y original value is multiplied with the scale factor. And in general, we can write this point, if the xy is the original point, now the x value remains the same and y value is made that many times as this stretch factor. The other scenario is if we have this y is equal to af of x, and a is between 1 and 0, then what happens? Then we call it the compression. As I said here, it becomes slow to fall and slow to rise. And in short, in more mathematical terms, it's called a compression. You are pushing it down towards the x-axis. So when A is between 0 and 1, it's a vertical compression. And here we have the vertical stretch. That's vertical compression by scale factor A. You can either say vertical stretch or stretch along y-axis by the certain scale factor. Right, up next we have question number 6 for the same task. It says investigate what happens in step 5 when the coefficient of x squared is negative. In the Desmos software, I got these two graphs. The graphs were y is equal to x squared. And now if we have to reflect it, if we have to make the coefficient negative, it clearly is a reflection. When the sign of the output is reversed, it's clearly a reflection in the x-axis. This original one is the y is equal to x squared graph. And when you have reversed the sign of the output, it's now the graph of y is equal to negative x squared. So guys, this is simply the reflection in the x-axis. It's more appropriate to say reflection in the line y is equal to 0 instead of saying x-axis, but both are absolutely fine. So if we have a point xy on the original graph, what will happen is the x value remains the same and the value of y is reversed in its sign, and that's all you need to remember for reflection in the x-axis. That is when you have the output being multiplied by a negative sign here. Next up is question number 7. It says predict what the graph of this would look like. So we can see, we can identify clearly. Let me write it again here. 2x plus 3 whole square minus 2. Let's see each of these numbers. This number that is multiplied with this original function. The original function was x squared. We also call it the root function. Alright, so I've written this original function here. This was a root function and we made changes to it to get this one. This number, as we've already discussed, that this number is accountable for the vertical stretch by scale factor 2. This positive 3 will be a horizontal translation. When you are adding, subtracting in the input, you get a horizontal translation, and since it is added, so that would be translation by negative 3. It means going 3 units in the backward direction. And this 2 is responsible for the vertical translation, and that is done by how many units? 2 units down. So this is going 2 units downwards. And if we combine these two transformations in a single vector, you'll say that this is translation vector negative 3, negative 2, and also it's a vertical stretch by scale factor 2. First, I'm going to sketch the original one. So it would look somewhat like this. And then we are going to translate it by negative 3 and negative 2. So this point here, the turning point, is now at negative 3 and negative 2. So here we are. And then I'm going to stretch it. By stretching, I would definitely make it more leaner, more quick to fall, and more quick to rise. That's my resultant here. So you can see what happened for each. First of all, the blue one is, the red one is the original function, the root function. And then this blue one is when we have done the translations. These are just the sketches. And then green one is when we have stretched this blue graph by scale factor 2. The original one is red one, and then it is moved backwards and downwards, as well as it is stretched along the y-axis. It's leaner than before. In question number 8, we are required to explain how this equation can be used to determine the location and shape of the equation. So first of all, this number A accounts for the vertical stretch, and that be a stretch if it is greater than 1. Otherwise, if it is between 0 and 1, that will be a vertical compression. In both cases, for A, we have the x point remaining the same and the y value being multiplied by this stretch factor. And this is for the stretch here. And then hk is the translation vector. Okay, so lastly, what we have here is this the sketch of these graphs. Y is equal to x squared, 2x squared, 0.5 x squared. This is the transformation that is obtained by multiplying the input. So if you have any original function, y is equal to f of x, the changes that you see here are in the inputs. What you're doing is this transformation. And as already discussed, when you're multiplying the input by a number, you are doing horizontal stretch, and the scale factor is 1 over a. That's the reverse way of remembering that. The scale factor is 1 over a. Let's see here. So we have the red one as the original graph. And now you can see that the red one is now pushed inwards towards the x-axis, or to get the green axis. It means it's a compression. So for compression, when you multiply a number that is more than 1, and similarly for 0.5, it's being stretched away from the y-axis. It's being stretched horizontally, but it's moving away. So we say that this is a stretch along the x-axis. By stretch along the x-axis, you mean to say that we are moving away y-axis. So what we notice from here is that if we have the original function y is equal to f of x, you are making the changes in the input. So we are doing y is equal to f of ax. What happens if this a is greater than 1? A horizontal compression, and the scale factor would be 1 over a. And for a to be between 0 and 1, it will be a horizontal stretch. You can see that if it's a decimal number less than 1, then it's moving away from the y-axis, so it's a horizontal stretch, and again by the scale factor 1 over a. Question number 9 says, do your findings from this investigation apply to the graphs of other functions? Generalize your findings. So these are the generalizations that we made, that if when do you have the vertical translation, when do you have the horizontal translation, reflection, vertical stretch, and horizontal stretch. And we made these generalizations, so I've already filled that. Now let's move on to the last question. Okay, so the last question says, how could these findings be applied in real life? Explain with examples. What we're doing is, when we are transforming, so suppose we have to design a dish. We have to design this dish so that it captures maximum amount of radio waves. And so this curve, if I show you from the side of this, the dish can be this, or it could be a bit more deeper than before, or it could be this. What we are doing is, in this case, we are basically stretching it along the y-axis. You can see that it is being stretched along the y-axis. So this is one example that is stretched or transformed. Another example is designing the tunnel. So you have the dimensions of containers. So for the huge trucks, what we do is we want the trucks to be able to travel not in the middle, but instead we want that we will consider the maximum height of each truck so that it can travel in one lane of this. Similarly, another truck can be coming at the same time on the other lane. So what we're doing is we want a certain height and certain width of this parabolic, or this parabolic curve. So again, the parabola, the transformations are used in order to determine how high should we go and how wide should we construct. Similarly, another application is for the transformation is when we are finding the optimal distance for a throw. So what we need to consider is the initial speed and etc. But again, what we need to consider is the parabolic path that it would cover. So we make transformations to the parabolic path using different values of launch angle and initial speed and initial height. Another application of this is when you're correcting the alignment of your teeth in your dental cavity in your mouth. So again, as you observe that these form a parabolic curve, and you would want these to be exact reflection of each other. Like this is the parabola that is made by the upper jaw, upper arrangement of the teeth, and you want each of these teeth to be exactly fitting on the teeth above. In short, what you're doing is you're reflecting it along the horizontal axis. So there is another application of the transformation of functions. Last but not the least, we have the modern day cartoonists making different cartoons or different characters using these mathematical formulae or functions at the background. So what they're doing is, let's say we just take a look at the pocket of Doraemon. This is a parabola, and we want this parabola to be in that certain place instead of being drawn here. What we're doing is we're shifting it down by certain amount, so that we are using the translations again. This is a circle, and we want the same size circle on the other side. So what we're doing is reflecting in the y-axis. The same eye is reflected about the y-axis, and so on. There are many transformations that you can see in everyday life, and this is one other example of that. I hope you enjoyed this video. You learned about the transformations of functions, and the generalizations that we made are applicable to all of the graphs. If you still have any problem, please write your feedback in the comment section. I will definitely get back to that. And if you have any other problems other than this topic, you can also communicate that to me in the comment section. Please like the video, and don't forget to subscribe my channel and hit the bell icon so that you are updated with the most recent videos that I upload. Okay, so instead of going through the video for each part of the discussion, what you can do is you can download the whole canvas. I have uploaded the whole canvas, the whole discussion in one page, and you can see that, you can access that in the description. The whole discussion is on a single canvas, and you can access it. Instead of scrolling through the video, you can see each of these discussions as a summary. Thank you.